Madam, are you hearing?
Cool.
Okay, that is going to happen in, that's going to happen in June 20th. June 23rd to 26th. There are 5 days of duration.
Okay, cool.
I would like you to, come and have us one more presentation if possible. Online again.
This June, I mean virtually?
Virtually to start with, we'll do virtually. Or if you can come down, I'll be very happy. I can put a budget.
Very hard to travel at this time.
Anyway, we will
send me an email. I'll be happy to do it if my schedule works out. I'll have to check my calendar.
Oh, sure.
But yeah.
Okay.
Definitely send me an email, then we can discuss offline about the time.
For sure. Thank you so much, madam. If you're ready, we can start the program.
Yeah, sure.
Okay.
Let me try to share my screen.
Okay. In the meantime, there will be a small introduction by our students to the gathering.
Yeah, feel free to start with the intro.
Yeah.
I'll try to put things together.
Ritika?
Hi, sir. Shall I start, sir?
Start.
Thank you, sir. Every day has its own bliss, and now with warmful hearts, I'd like to welcome our speaker, begin to this evening with delightful moments. And we extend our welcome to the special guest, Dr. UGT, Professor, Department of Electrical and Computer Engineering, Carnegie Mellon University. Our brains turn into simple signal processing units, quickly spreading information into conscious and then back out again. I thank Dr. N. Kumarappan sir, Chair IEEE Madras Section, Dr. N. Venkateshwaran sir, IEEE Madras Section, SPS Chairman, and lastly, Dr. S. Brinda, IEEE Madras Section, SPS Vice Chair, for providing this important opportunity. Now, with no more let's enter into the session, and I request Brinda ma'am to address. I request Venkateshwaran sir to address the gathering. Please, sir.
Yeah, I join with you to invite our special guest today, Dr. UGC from Carnegie Mellon University. I think one of you can read out the biodata. If madam's biodata there, it is already there. Can I do that?
Yes, sir. Sure, sir.
Yeah. So, yes, 1 second, and there is some small delay. I think I have with me right now. Okay. Yeah, sorry for the small delay, but I'm just locating the file.
No worries.
Yeah, I got it. So, Dr. UGC is a professor in Department of Electrical and Computer Engineering and a faculty affiliate with the Machine Learning Department and Scilab at Carnegie Mellon University. She received her PhD and MA in Electrical Engineering from Princeton University in 2012 and 2009, and B Honors in Electrical Engineering from Tsinghua University, Beijing, China in 2007. After a stint with the Ohio State University from 2012 to 2017, she is with the Department of Electrical Computer Engineering at Carnegie Mellon University since 2018, where she is now a professor with a courtesy appointments in the Machine Learning Department and Scilab. At Carnegie Mellon, she held an inaugural Robert E. Dothry Early Career Development Professorship from 2018 to 2020. A research interest is in the theoretical and algorithmic foundations of data science, signal processing, machine learning, and inverse problems, with an application in sensing and societal systems, broadly defined. Among others, she is a recipient of a Presidential Early Career Award for Scientists and Engineers, the inaugural IEEE Signal Processing Society Early Career Technical Achievement Award for contribution to high-dimensional structural signal processing. IEEE Signal Society Young Author Best Paper Award. She was named a Goldsmith Lecturer by IEEE Information Theory Society and a Distinguished Lecturer by IEEE Signal Society. She is currently serves as an Associate Editor for IEEE Transactional Information Theory. Also, she is serving as an Associate Editor in IEEE Transactional Signal Processing and also in IEEE Transactional on Pattern Recognition Machine Intelligence, PAMI, and Information Inference, a journal of IMA. With this broad introduction, I welcome Dr. Chi to present her talk.
Thank you so much for the very kind introduction, for the invitation. It's my great pleasure to give the lecture today. The topic is on spectral methods for data science. So to begin, I'll just give you a little bit of background on the topic. So actually earlier, I think probably late last year and earlier this year, we published a monograph on this topic called Spectral Methods for Data Science, a statistical perspective, joined with my colleague Yuxin Chen, who's currently at the University of Pennsylvania, Jianqing Fan at Princeton, and Cong Ma at University of Chicago. So the talk I'm going to give today can be sort of thought as a small teaser for the sort of flavor of the topics we've been covering in the book. And if you're interested in today's presentation, I hope you can go actually read our book a little bit as well. Sort of a preprint version of this book is also available on arXiv, so you can find it sort of for free. All right. So the broad motivation of studying spectral methods really boils down to understanding data. So you might heard the word data deluge or big data, because we now have a lot of different sensing and imaging modalities that allows us to propose a nature in different fields of science and engineering in manners that were not available before. This boils down, range from applications in, for example, in healthcare, in radio astronomy, for network monitoring, seismic data, and some of the microscopy data, for example. So this large amount of data really brings a lot of opportunities, but also bring challenges from the single process and machine learning perspective, that we now need tools to sort of derive insights from this data that are scalable in terms of both computation and memory use due to the large scale of the data set. All right. So it turns out that for many of the problems that we're interested in, if you arrange the data properly, some sort of low dimensional structure will pop up. So what I mean is that often we will be thinking of the data that we have at hand arranged in some form, say, of a matrix. And if you look at the spectral structure of these matrices, there are some sort of low rank structures, where the spectrum of the matrices typically has a fast decay or only a small number of components that corresponds to large eigenvalues or singular values. Such low rank structures and the components that corresponds to this large singular values or eigenvalues often correspond to useful latent information that we are interested in figuring out sort of structures or understanding the problem at hand. So to give you a little bit of flavor of what I mean by low rank structures in data matrices in general, I'm going to talk about this sort of small example on community recovery. In the book, we actually cover a lot more different sort of applications where spectral methods can be applicable. But within the context of the presentation, I'm going to look at this community recovery problem, which is sort of a simple prototypical application. All right, so what is this community recovery or graph clustering problem? Community structures often pop up when we are studying social networks. So imagine we have many users in a social network, and these users can be connected based on their interactions. So what we will typically think of this is a sort of a big graph where every user corresponds to nodes of the graph, and we will have edges between the nodes or between the users based on how strong their interactions is. And the goal of community detection or graph clustering is to partition these users into several clusters based on, say, their friendship or their similarities or their interactions. So mathematically, this sort of community recovery problems can be modeled using this mathematical model called stochastic block model. So without loss of generality, consider a simple case where we only have two communities. And we have n different users, each represented by a node in the graph. And we're going to think of these two communities to have equal size, just for simplicity, where let's say the top half nodes corresponds to the first community, and we're going to assign a label to them as 1. And the bottom half of the nodes corresponding to the second community, and we're going to assign a label to them as -1. All right, so we do not know these labels, but we only observe the graph, and our goal is to sort of recover the labels based on the graph observation, right? So how do we populate the edges in this stochastic block model? How do we model the interactions based on the underlying memberships? So the way this is being done is by assigning these edges corresponding to a Bernoulli distribution, where the parameter of this Bernoulli distribution is based on whether the two nodes at hand are within the same community or not. So in particularly, our observation here will be a graph. And if you take a pair of nodes I and j, and these two nodes will be connected with probability p if they are within the same community. But if they're not within the same community, they will be connected with another probability q. So without less of generality, we're going to think p to be usually greater than q. So nodes within the same community will have a higher probability of being connected than nodes that are not in the same community. And the difference between this p and q roughly tells us sort of distinction, right, between the community members. And the goal here is to recover the community membership of all the nodes. In other words, the underlying labels of the nodes based on the observation of this graph. Right, so this is sort of our basic problem that we want to study for community recovery underlying this model, very simple stochastic block model. All right, so equivalently, we can actually represent the graph observation using its adjacency matrix. And this matrix is nothing but a big binary matrix of size n, where n is the number of nodes, and the entries in this adjacency matrix are drawn corresponding to this Bernoulli distributions, where the parameter again of this Bernoulli is determining whether the two nodes belong to the same community or not, right? So basically, you can think of this matrix A is a random matrix where its realization is based on how these edges are drawn according to the stochastic block model. So because this is a random quantity, we can study its sort of population variant. Or we can decompose this random matrix around its population version. That is the expectation of this matrix, plus some perturbation corresponding to the fluctuation of this matrix A around its population version. All right, and interestingly, the population version of this matrix, which is the expectation of the adjacency matrix, has a very interesting block structure that is corresponding to the underlying community structure. So in particularly, with a little bit of simple calculation, you can see this population variant of the adjacency matrix is in fact a rank 2 matrix, where the spectral component corresponding to the largest eigenvalue is essentially uninformative. It's something that gives you a bias that's corresponding to an all-one matrix. While the second component, which is actually more interesting to us, is where the eigenvector actually tells us nothing but the underlying community structure. Okay, so actually the second component will be what we will be primarily interested in if we're interested in digging out the community structure. So this actually reveals a natural approach to figuring out the community structure using the spectral property of our matrix A. So in particularly, we're going to do this sort of naive version of the spectral method, where we are going to first remove the uninformative bias from our observation adjacency matrix A, and then compute the leading eigenvector of the bias removed version of the adjacency matrix, which, based on our understanding earlier, should tell us a lot about the underlying community structure. So once we find the leading eigenvector U, we can simply declare the community memberships by doing a rounding procedure of the eigenvector, where we'll essentially declare the memberships based on the sign of the eigenvectors. So if Ui is greater than 0, we'll declare a membership of 1, and if it's smaller than 0, we'll declare a membership of -1. Okay, so if a careful reader might see that this sort of mean subtraction might be not very realistic, because it actually requires us to know the value of P and Q, which we might not know a priori. So this is just down here for simplicity. In fact, you can also directly extract the second eigenvector of the matrix A, which will also directly tell you the membership, the community structure. But for simplicity, we'll be discussing primarily this version that we will subtract the mean first, and then compute the top eigenvector of the mean subtractive matrix. All right, so again, the rationale here is if this perturbation size is small, then this top leading eigenvector will tell us a lot about the community structure. Indeed, if our matrix A is exactly the population variant, then the top leading eigenvector will be actually proportional to this vector 1 minus 1, which will be corresponding to perfect clustering. So at least the spectral method provides some sort of intuitive method, which is very simple to recover the underlying community structure. And often when we perform this spectral method, we only need to compute a few number of top eigenvectors, which can be done very efficiently, for example, using the powers method. So often the spectral method can be computed in a very efficient manner, even when the underlying problem size is very large. Just to recap what we are doing here, a general recipe for the spectral methods typically follow this sort of 3 key steps that we will be primarily thinking of the data as some sort of random realization of some underlying data drawn from some underlying probability distribution. And if you study this sort of population variant of the problem, often you can identify some key matrix that say we call M star. And this M star often have some sort of low rank structures where the top eigenvectors will disclose some very crucial information we are interested in identifying, corresponding to key quantities such as underlying community structures for our community recovery problem. And often in applications, we will not be able to directly observe this key matrix M star, but often some sort of random realization or surrogate version of it based on data. So our hope is M will be close to M star in certain metric, but it may not be an exact version of M star due to constructing the surrogate matrix based on data. And we are going to actually compute the eigenvectors of this surrogate matrix M as our estimate, which hopefully will be close to the eigenvectors of M star, therefore providing a sort of faithful estimate of the crucial information we are interested in. So this is sort of the very simple and general recipe of the spectrum methods that you actually see being applied to a large variety of different applications in practice. So here I'm just showing sort of a laundry list of possible applications that you can apply the spectrum method. And this is, in fact, I'm sure many of you already know about this, but just to provide a little bit of background to make sure everyone is on the same page, let's consider the problem where the underlying matrix of interest is a symmetric matrix. So the sort of the true matrix that has a low rank structure we're interested in. Let's say that one truth matrix is M star, and we also have a perturbed version of this matrix called M, and the perturbation matrix is denoted by a matrix E. Okay, and both matrices has this eigen decomposition where we denote the eigenvectors of the matrix M star by U stars. And we denote the eigenvectors of the perturbed matrix M as vector U's without having the star. So every time you see a star that corresponds to the ground truth we're interested in, everything without the star corresponding to the things derived from the data. Okay, in particularly often we only care about sort of the top components. So just to write out this a little bit more clearly, when you arrange the eigenvalues in sort of a descending order, so here let's think of M star as positive semi-definite, so we don't need to worry about the signs. We'll be primarily interested in sort of the top R component so we're going to call U star essentially the collection of the eigenvectors corresponding to the top R eigenvalues. And the rest of them will be sort of this U perp star that is often not of interest. Okay, so the goal here is basically try to estimate U star using the spectral decompositions. All right. So the question boils down to basically we want to understand how the size of the perturbation E affects the distance between U and U star. Right, so we extract the top eigenvectors from the matrix U star, from the matrix M star, and we extract the top eigenvectors from the matrix M. Both of them I call U and U star. I want to relate the distance between U and U star to the size of the perturbation. Right. Before we go there, we have to come up with a proper way to measure the distance between the two subspaces U and U star. So obviously, we cannot directly measure their distances in terms of, say, Frobenius norm or spectral norm, because they do not directly account for the global orthonormal transformations. What do I mean by that? This really just means if you take any orthonormal matrices, if you look at the subspace spanned by the column of the matrix U, it will be the same as the subspace spanned by the matrix U times R, where R is any orthonormal matrix. So when we measure the distances between the subspaces, we have to take into account this global orthonormal transform in this ambiguity in the representation of the subspace. So a simple fix of this is just measuring the distance by taking into account this orthonormal transforms. In other words, we'll be measuring the distance between UR and U star and looking at all the possible orthonormal transforms and taking the minimum of this distance. Okay, so we could be either looking at the distance measured in spectral norm or the distance measured in Frobenius norm. For the purpose of the talk, it doesn't really matter which one you need. Often they are equivalent up to some sort of constants. All right, so what do we know about this perturbation once we know how to measure the distances between the subspaces? Classically, this boils down to this very well-known theorem developed by these two gentlemen, Davis and Kahan, called the Davis-Kahan sin theta theorem. So the simple version we'll be discussing here is basically the one we put on the slide. Let's say the underlying ground truth matrix is positive semi-definite. If we know the size of the perturbation is smaller than this quantity, which is a small constant times the spectral gap between the R's largest eigenvalue and the R plus 1's largest eigenvalue, then we can actually bound the distance, which roughly speaking is proportional to the ratio between the size of the perturbation and the spectral gap. So in other words, the distance will become larger. The perturbation in the subspace becomes larger as we increase the size of the perturbation, which is intuitive, and also as we sort of decrease the spectral gap. So in other words, the spectral gap sort of tells us how hard we can distinguish maybe the R's eigenvector from the R plus 1's eigenvector, right? So this sort of is intuitive result in some sense that these two quantities, the perturbation size and the eigengap, determines critically the performance of our spectral method in terms of L2 perturbation. All right, so how do we perform this spectral analysis on top of the community recurrent problem we talked earlier on this stochastic block model? So just recap what we had before, and without getting into the details, all we need to do in order to execute the Davis-Kahan theorem to the problem is actually to bound the perturbation between the affinity matrix that we draw from the stochastic block model and to its population version. And turned out that under some very mild assumptions, essentially this quantity is bounded on the level of square root of n times p, where p is a Bernoulli distribution corresponding to the in-community distribution. All right, so with this perturbation bound in hand, you can directly plug this into the Davis-Kahan theorem and immediately bound the distance between the top eigenvector u and u star, which is roughly on the order of the quantity on the right, which is on the order of square root of np divided by p minus q times n, as long as the denominator is significantly larger than the numerator. All right, so what do we mean by this? So this means if we can guarantee the denominator is much larger than the numerator, right? In other sense, if we can guarantee the right-hand side quantity goes to 0 asymptotically, then we can essentially ensure the top eigenvector that we are extracting based on the data will be close to the ground truth community structure vector u star asymptotically. So this quantity will be much smaller than 1. It goes to 0 asymptotically, and this will imply essentially near perfect clustering. All right. So what can we say about this assumption, this condition that we just derived? In the dense regime, when the graph is dense, when both p and q are sort of on the order of 1, this condition essentially can be reduced to that the difference between p and q only needs to be larger than on the order 1 over square root of n. And this is much smaller than the order that we are putting on p and q. So that means p and q can be very large. So all these nodes are being heavily connected. So the graph looks very dense. But as long as the difference is on the order 1 over square root of n, we can actually do an almost perfect clustering, indicating the difference can be made much smaller than the connectivity. Alternatively, in the sparse regime, where we set P and Q on the order log n by n, which is sort of the lower bound, the level you need for the graph to be at least connected, this can be essentially boils down to reading as a condition that A minus B is at least larger than square root of A times log n. So again, this is saying the difference between A and B, which maps to the difference between P and Q, only needs to be roughly on the order square root of A, again, much smaller than the level that we're setting on A and B. So this basically suggesting the spectrum method can actually work quite effectively as long as the difference in the connectivity is larger than a threshold that is often much smaller than the actual in-community connectivity, or basically then there's a quantity P and Q itself. So these conditions is actually turned out to be information theoretically optimal, suggesting that the spectrum method, despite being very simple, particularly in contrast to some other possible classical methods that you may have in mind that may invoke much more computationally expensive procedures such as semi-definite program, the spectrum method is actually information theoretically optimal, indicating you might not need to resort to much more complicated methods, much more computationally expensive methods for solving this problem in the stochastic block models. All right, so enough about the sort of benefit of the L2 method. And indeed, when you run this method for this SBM model, you see you do observe this kind of threshold phenomenon that as long as the difference is sufficiently large, we can get very good clustering results. However, this L2 perturbation theory is not satisfactory in the sense we may not be able to get or to explain exact recovery phenomenon in the sense that we want to actually be able to say something stronger in the sense we can simultaneously recover the memberships of all the nodes. So we want to say something about the individual nodes, not just on population level, on average that we can recover the community, but we want to say something about the individuals, right? So this is a much finer grained and much stronger guarantee we are looking for. Something that this L2 recovery theory cannot offer. So what do we need if we want to say something stronger in terms of recovering the membership of all the nodes? So to do so, we actually need to be able to say, to use our infinity theory. So why is that the case? So let's do some reverse engineering here. So spectral recovery actually uses the sign of the eigenvector to cluster the nodes. Right? That means that we can say exact recovery if for each entry of the eigenvector, ui has the same sign as ui star. So in other words, the product is greater than 0. That is what we mean that they have the same sign. And note that we know this vector u star is actually is essentially a constant within each membership, right? So we can actually guarantee ui has the same sign as u star as long as we can guarantee u is not too far away from u star in an entry-wise version. So because the entries of u star is put around the order 1 over square root of n, this is essentially saying we want the entry-wise error to be smaller than 1 over square root of n. And this can guarantee essentially u will always have the same sign as u star at every entry. Okay. So this sort of our infinity non-bound naturally pop up if we want to say something entry-wise about our community recovery. And therefore, we will need an L infinity perturbation theory in order to get such bound. All right. So how do we do this kind of fine-grained L infinity perturbation theory for our problem? And what sort of additional challenge we may have? All right. So to do this sort of, I want to just begin with a toy example, sort of put ourselves away from the community recovery problem a little and look at a slightly simpler problem on rank 1 matrix denoising. And this is sort of mimicking the problem we have in the community recovery problem, where the underlying ground truth matrix is a rank 1 matrix, let's say with the eigenvector u star and eigenvalue lambda star. And we have some sort of noisy version of this rank 1 matrix, where the noise is some sort of Gaussian noise that has a symmetric structure, and the variance of the noise is sigma squared. And we're going to estimate u star based on the leading eigenvector of this observation matrix M, and we're going to call our estimate E. And here the goal is to characterize this entry-wise error in estimating u star, because we cannot identify the sign of the vector u star. We're going to think of the entry-wise error as taking the minimum of out of these two different variants of the infinity norm errors. All right. So this is a problem we are interested in. Now, before we go to the L infinity norm error that we are going to develop, let's just look at what we can get from our classical L2 perturbation series that we just studied earlier. Now, to quantify the size of the perturbation, this is something that's sort of easily done by just invoking the standard result in high-dimensional statistics, that the spectral non-perturbation of the noise is roughly on the order of sigma times square root of n. Okay, and putting this in hand with the Davis-Kahan sin theta theorem, we can immediately see the L2 distance between u and u star is essentially bounded on the level of sigma times the square root of n divided by lambda star, which is the eigenvalue of the matrix M star. All right, so as we know directly from the norm relationships, the L infinity norm, which is measuring the entry-wise errors, is upper bounded by the L2 norm. So immediately we can actually bound the entry-wise error by the L2 norm, which is on the order square root of n times sigma divided by lambda star. However, if we know that if the errors between the eigenvector is sort of evenly distributed across all the entries, there is a possibility, a chance when this L infinity norm can be much smaller than the L2 norm if the errors are evenly distributed. And that is sort of where we are targeting, right? We want to see if there is a scenario when the L infinity norm can be actually bounded in a much tighter fashion than just simply naively invoking this norm relation. So when is that possible? As we are hinted on, we want to targeting a scenario where the error may be evenly distributed across the entries of the vector. And this turns out to be also related to when the underlying ground truth vector u star also has an energy that's sort of distributed evenly across its entries. And to measure this sort of energy distribution, we're going to look at what we call the incoherence of the vector u, which is basically looking at sort of the L infinity norm of the eigenvector u star itself. So if we think of the vector u star as a unit vector, and let's say we define its incoherence as n times the square of its L infinity norm, then this parameter mu essentially lies between the interval from 1 to n. And there are essentially two extreme cases, right? So one extreme case is when the energy of this vector u is only centered in one entry, let's say the first entry as E1. And in this case, The incoherence essentially is the largest possible corresponding to n. On the other end, if the vector u star has all the energies evenly distributed across all the entries, for example, like an all-one vector or sort of the community structure we've seen in the community recovery problem, then the coherence parameter mu is going to be the smallest possible as 1. So roughly speaking, the smaller the mu is, the more evenly distributed the energy of this vector u star across all the entries. So in our problems, we'll be often thinking of mu as some small constant corresponding to scenarios where the energy of the underlying eigenvectors are more or less evenly spread across the entries. And this is where our L infinity theory will sort of give us a bigger gain. Okay, so let's look at what we will be able to derive for this problem. Okay, so the theorem is essentially the following. Under the sort of the condition where the L2 infinity, the L2 perturbation theory can kick in, we can actually bound the L infinity norm between u and u star at this level. Okay, where you see that this is on the level of basically sigma divided by lambda star times a scaling factor that's the sum of square root of log n and the square root of mu, where mu is the incoherence parameter we just defined. So indeed, whenever mu is not larger than the order of log n, corresponding to scenarios where the entries of the vector u star are having somewhat similar amplitudes, the bound essentially reads on the order of sigma times square root of log n divided by lambda star. And this is much, much smaller than the naive bound we can derive based on the L2 theory, which is on the order of sigma times square root of n divided by lambda star. In fact, it is better by a factor of square root of n divided by log n. So remember, in large scale problem, typically n is going to be very large. Therefore, this sort of improvement is actually very significant. It essentially amounts to distributing the L2 error almost evenly at every entry, so we can reduce the bound on the L infinity norm almost by a factor of square root of n. All right. So how can we get such a bound, and what is the technical hurdles? So let me just explain this briefly, just to give you some intuitions. The main bottleneck is to try to understand the entry-wise behavior of the eigenvectors. So let's say I want to understand, say, the L's entry, UL. And because the vector U is an eigenvector with the matrix M, I can actually sort of pull out the L's entry by writing it as such, right? Now, the difficulty here really boils down to the fact that the eigenvector U, because it is computed based on the data matrix M, it is actually dependent with the noise matrix E. So when we try to bound this quantity that we have, this turns out to be very challenging and prevents us from invoking all the nice concentration inequality that we know from high-dimensional statistics due to the complicated statistical dependencies between the entries of the vector E with this sort of row vector that we have that also includes the matrix E. So directly bounding this will be very challenging due to this complicated statistical dependency. It will not give us the type of tight bounds that we want from the previous slide. So how do we handle this? Because the difficulty here really lies in the complicated statistical dependency between the vector U and, say, the L's row of the matrix E when we do this inner product. We would like to try to let's construct some proxy, say UL, which is independent with a row vector, but at the same time close to the vector u that we want to that we are interested in. So if we can construct this proxy and decompose this quantity we are interested in bounding into two terms, where in the first term, ideally, we'll be able to exploit the statistical independence between UL and EL, so that standard the concentration bound can kick in to give us tight results. And at the same time, we can also leverage this independence to sort of control the proximity between U and UL, so that we can actually bound the second term also in a tight fashion. And then we will be able to actually control the original quantity. Okay, so that is sort of our plan. The plan is to introduce some sort of independent proxy of the original spectral estimate. And to do this, we introduce this sort of very powerful leave-one-out machinery. The way we are going to do this is we are going to introduce one sequence for each entry in the spectral estimate we are interested in. And we're going to construct this new matrix, this auxiliary matrix that you will never construct in practice, but only useful for the theoretical analysis, called ML. And this ML matrix is essentially the same matrix as the original data matrix M, except we're going to replace the else row and the else column by the clean data. So we'll be removing out all the noise in here. Of course, we cannot construct this ML in practice because we will not know what the ground truth is in that row and that column. But this ML will be very useful for analysis because now on the else row, we are essentially removing the noise and seeing the ground truth on that. All right, so why is this useful? So let's see a little bit about the analysis. So let's call lambda L and UL respectively the leading eigenvalue and the leading eigenvector of ML. And clearly by construction, UL is actually independent with the noise entries in the else row and else column. All right, because UL is actually obtained by dropping out only a tiny fraction of the data, right? It is only different from the original problem on one row and one column. We expect UL actually to be extremely close to the vector U, okay? Due to this sort of leave-one-out construction. On the other end, by construction, if you study the else entry of this leave-one-out version, due to this leave-one-out construction, we can actually replace the ML here exactly by M star, the ground truth, because on the else row, there is actually no noise. So the noise never occurs in understanding the else entry of the leave-one-out variant. And by writing out what the ground truth is on the else entry, we can actually control this last quantity by using our L2 perturbation theory, because we know lambda L will be close to lambda star, and the inner product between U star and UL will also be very, very close to 1. So we can actually show the else entry of this leave-one-out quantity will be very close to the else entry of the ground truth. And then by doing essentially triangle inequality to pass on this proximity of the around the else entry between UL and U star, we can control now the else entry of the data, the eigenvector derived from the data around the else entry of the ground truth. All right, so this is essentially where this leave-one-out estimates becomes useful, because it creates this sort of bridge to handle the statistical dependencies that is difficult to deal with if we try to do it directly. All right, so enough about the theory. Let's just look at how this boils down to the community recovery problem. So as hinted earlier, by using this sort of L infinity error bound, we can actually get a much stronger sort of exact recovery guarantee. And in particularly, we can look at this in this sort of sparse regime where we sort of pose our connectivity probability P and Q on the order log n divided by n. And as I mentioned earlier, this is sort of the connectivity that you need just for the communities to be connected. And we can actually get very sharp bound in the sense we can guarantee exact recovery as long as the following formula holds. So the square of square root of alpha minus square root of beta is greater than 1. It's greater than 2. So to put this differently, it turns out that this essentially certifies the optimality of the spectrum method, because we also know that if this threshold is below 2, then actually no method whatsoever can achieve exact recovery. So indeed, this indicates a sharp phase transition phenomenon. This quantity here is actually by no means a coincidence. It turns out that you can actually interpret this quantity as a Hellinger distance between the Bernoulli distributions between the two communities, between the in-community distribution and the cross-community distribution. So in other words, if the squared Hellinger distance between the two Bernoulli distribution is greater than 1 times log n divided by n, then the spectrum methods work. And once it's below, then essentially no method can work. So this is basically suggests the spectrum method is optimal for community recovery in this sort of stochastic block model. And there is no need to resort to more computationally expensive methods for resolving the communities for such model. All right. So spectrum method so community recovery is by no means the only application that we can apply this kind of L infinity error bounds. So just as an illustration, let me just quickly mention another application on low rank matrix completion. And what is this low rank matrix completion problem? So this is a problem that has been sort of heavily studied in the maybe last decade-ish, where the goal is try to recover the underlying low rank matrix just from a small number of entries, a subset of entries of this matrix. And again, we're going to assume the entries observed independently with some probability P. And instead directly sort of estimate the whole matrix, we're going to targeting some somewhat intermediate goal for the spectrum method here, where the goal is to estimate sort of the subspaces U star and V star, corresponding to the column space and row space of this matrix. So spectrum method typically is often used as, say, some sort of initialization for more involved iterative optimization schemes to estimate this low rank matrix. So what can we say about the spectrum method here? So very simply, we can invoke our general recipe for this matrix completion task. And we can construct this sort of surrogate matrix, which essentially is this partially observed matrix being scaled by a constant 1 over P. This just ensures that if it takes the expectation, this gives us M star. And then we can compute the rank R SVD of the matrix M and return all the sort of salient quantities as our estimate. All right. So what do we know about the performance of the spectrum method for matrix completion? So here we're just directly giving you what we get from the L2 error, L2 perturbation theory and L infinity perturbation theory. And again, in this theorem, we will also have some sort of incoherence metric, very similar to the version that we defined for the rank 1 matrix, but more or less a more general version when we look at rank R subspace. And without getting into the details of the all the quantities. Let's just try to interpret this in the regime where, let's say, the incoherence and the condition number and the rank are all sort of small on the other one. And just focusing on how the bound scale, say, with respect to the dimension of the matrix N. So again, we see that the L infinity norm is actually much smaller than the L2 bound by a factor of 1/n. Again, indicating that when the underlying matrix has its energy distributed somewhat evenly across all the entries, we can actually also bound the entry-wise error in a much tighter fashion compared to naively invoking the L2 theory. And such L infinity norm is actually very useful for problems such as matrix completion from an operational point of view. For example, considering a prototypical application of matrix completion in recommendation systems, where essentially every entry in the matrix will be corresponding to some sort of rating or score of a user for a certain product. And this sort of L infinity norm bound essentially allows us to actually pinpoint the estimate of the specific ratings for a specific task or specific object from a particular user in a very precise manner, because now we can actually control sort of this entry-wise error by using this sort of L infinity error controls. So if you are interested in seeing more details, you can sort of visit our book that covers a lot more details. So within this presentation, we just sort of give you sort of a very bird's-eye view, just looking at sort of the tip of the iceberg for understanding the spectral methods for many different problems in data science from a statistical perspective. There are a lot of other topics that I haven't covered, such as studying more applications of the spectral methods for different problems. And there's also a lot of interest in looking at uncertainty quantifications, trying to give confidence intervals for these spectral estimates. You could also try to study precise asymptotics of the spectrum estimators. There are also a lot of different variants that goes beyond this vanilla version of the spectral analysis that may have certain advantages. For example, if the data is corrupted or have heavy tail noise, then you may want to actually invoke some other variant of the spectrum methods that give you better performance. All of this I sort of discussed in the book, but for the sake of time, I won't be able to talk in depth in this presentation. I hope this talk give you a little bit of flavor about what spectrum method, what kind of problems spectrum method can tackle, and what kind of performance guarantees we can say about the spectrum method. If you're interested in learning more, you can visit our book that has been just published by the Foundation and Trends in Machine Learning. With this, I'll conclude my talk. I'll also thank my funding agencies that support this line of research. If you're interested in seeing some more papers and the book, you can also find them on my website. So with this, I'll conclude. I'll be happy to answer any questions you have, and thank you so much for your attention.
Thank you, Professor Shi, for a wonderful talk on this subject of spectral methods for data science. There are a couple of questions that people have asked on the chat box. Can I just put it across?
Yeah, sure.
Yeah. Can you please say where to find the data set to work with spectral methods?
I mean, it certainly depends on the application, right? For example, for recommendation systems, you can use Netflix data, movie lens data. All these data sets are publicly available online. I believe for ranking problem, there are also many different data sets online. Yeah, so I encourage you to try out the methods for the application you have on hand. And often, I should mention that spectral methods often is used also as sort of intermediate or initialization scheme for you to use for that often will be served as initialization for a second stage that invoke more computationally expensive methods. So for example, it can be used as an initialization for gradient descent, for alternating minimization in applications such as matrix completion. But it will typically, in some applications like the community recovery problem, it turned out it is already optimal, so you don't need to invoke more computationally expensive methods. But generally, in more sophisticated methods, you may still need a second stage. But regardless, spectral method can be very helpful to for you to get an initial good estimate of the problem.
Thank you, madam. Can I have one question from my side?
Yeah, sure.
Now, I just would like to know that, you presented the L2 perturbation theory. Now, is it boils down to the distance computation between U and U star, boils down to, optimal choice of the R value?
Oh, what value?
R, you have an R value, no? This small
Oh,
R.
yeah. So R is typically something that you prescribe, right? For example, in community recovery, the rank is 1, right? You're looking at the top component, so the rank is given. Often, if you're looking at applications such as principal component analysis, then actually R is sort of a hyperparameter, right? If you want to determine what is the dimension you want to use when you invoke some dimensionality reduction procedures. And often what people do is actually examine the spectral gap, right? That if you want to sort of cut off the R at a place where the spectral gap is large, and that sort of is relevant to in the Davis-Kahan theorem, where a larger spectral gap is sort of helpful.
Okay, ma'am, thank you. Again, in the theory, L infinity perturbation theory does not involve, the values of P and Q. The distance computation does not involve P and Q.
Yeah, so here we're doing a sort of example in this rank-1 matrix recovery problem, right? Okay. When you actually invoke this theory for
22, slide number 22.
For the community recovery problem. So I actually had the detail about how that result is being applied. There's additional mathematical details because you will then essentially all the parameters, the coherence parameter, and this will be relevant to this P and Qs, right? So when you actually invoke the theory, there's actually additional details in the application. It will read a little bit more complicated than what I actually make it look like in the slide. But yeah, that's a good question.
Okay, one last question. How do you compare your theory with matrix recovery using sparse models like dictionary learning?
So dictionary learning is tackling a different class of problems, right? Like exactly like you said, it's kind of sparse coding problem, trying to find sparse representations. Here we are not solving the same problem, right? It depends on the problem you are solving. I feel they are not looking at the same problem. So it's not like directly comparable. It's like comparing apples with oranges. So
in terms of performance, in terms of recovery, complete recovery, in terms of performance, yeah.
So what kind of problem are you looking at for dictionary learning? Because my understanding is
denoising problems.
So these are not applied to images, right? Yeah, you have to give me a sort of more precise model in order to compare this. The spectrum method we are looking here is kind of more general, sort of in the sense, it give you a general recipe to tackle different problems, right? And you can apply this as needed for the problem at hand by sort of interpreting or bounding the perturbation. So if for different problems, you will have different perturbation bounds. And when you plug into sort of this maybe umbrella results, you get different guarantees. For this particular toy problem on rank 1 matrix denoising, I don't think this is a problem that you will invoke dictionary learning because there is no sparsity structure. This is a very simple problem. Yeah.
Yeah. Thank you so much, madam. Are there any questions from other participants, please? Are there any questions from other participants? You can unmute and ask, or you can put it on the chat box. If there are no questions, I request the Vice Chair of IEEE Madras section, Dr. Brinda Swaminathan, to probably give a word of thanks to Madam. Are you there, Madam? Yeah. Yeah, please unmute and talk. Yeah. Vice Chair, Brinda?
Yes, sir.
Yeah. Yeah, you can probably give a lot of thanks to Madam, having spent from, long, so long. Yeah.
Yes, ma'am. Good evening. Good evening, ma'am. Audible?
Yeah, good evening.
Yeah, ma'am. How are you?
Good. Yeah, thank you so much for having me. It's a great honor to be here virtually.
Your talk is very nice, wonderful.
Thank you so much.
Yeah, we had a healthy discussion today with you, ma'am. Thank you very much.
Thank you so much for having me.
Yeah, on behalf of IEEE Madras chapter, Signal Processing Society, we are very much thankful to Dr. UG Pei, Madam, for giving us the wonderful talk today for the participants. Thank you very much, ma'am. We will meet with one more program very soon.
Thank you. Thank you for having me.
Thank you, Madam. Thank you. I'll invite you for a different occasion, Madam.
Yeah, just send me emails. We can discuss the time offline.
Yes, thank you.
All right. Thank you so much for having
you,
me.
ma'am.
It's
Thank
really
you.
nice. Thank you. Goodbye, everyone.
Bye.
I think, yeah.
Thank you, participants.
Thank you, Madam. Thank you so much, Brinda, Madam, for organizing so nicely.
Sir, I was so late today.
Oh, that's okay, but see, we all have multiple work, among this we are doing this, right?
Yes, sir. And this is unexpected work for me today.
Yeah. There is Dr. Dhanlakshmi from SRM. How are you, Madam? Still there? Dhanlakshmi?
Dhanlakshmi, ma'am, are you there?
She's there, actually. Vinod Kumar, sir. Thank you for participating. Charu. Yeah. I think we can wind up.
Your known circle, sir?
Some of them are known to me. Some of them, this faculty. Vinod Kumar, sir, is my colleague.
Okay, sir. Nearly 60 participants I have seen.
Yeah, maximum of 67 actually. That's somewhere around 67.
Something I cannot unmute.
Oh, you're not able to unmute. Why?
Only because the host and the co-host only can unmute, sir.
Oh, okay.
That's settings in the Zoom.
Oh, sure. Okay. They gave me chance to speak.
Yeah. Aditya, just unmute all. Can give a setting, change the setting. And at the end of the talk, we can change the settings, sir. That's for better. They can interact very well with the speaker. Next time I will take care, sir.
Okay, ma'am. Okay. Thank you, madam. Shall we say officially this meeting is closed?
Yes, sir.
Okay.
Thank you all.
Thank you, ma'am. அவங்க கூட வந்திருந்தாங்க KCT Kumaraguru College of Technology. She was there actually.
Okay, sir. Many people are in the meeting. Joe, something. Different people are there in the meet, sir. Other than Sairam.
Yeah, there are a lot of people. Good.
Yes, sir.
Thank you, madam. Thank you.
Thank you, sir. Thank you.
Will I leave?
Yes, sir. Aditya? Ritika?
Yes, ma'am.
Yes, you can leave the meeting, close the meeting.
Okay, ma'am.